So as we're jumping into cardiac physiology, the actual function, one of the things I like to point out to students is our heart is not the same as every other animal's heart. So I was thinking this is for Jamie. She's not even in this class. Fish have two chambers in their heart, right? Amphibians have three chambers. Reptiles have four chambers, but the septum, the wall between their ventricles is incomplete. So it's kind of, is it three, is it four? It's really only birds and mammals that have four chambers in their heart. Thoughts on why? So it basically seems like increased metabolic demands demand more chambers. So we end up with these two pumps side by side so that one can deal with pulmonary circulation and one can deal with systemic circulation. Fish, which are a cold-blooded animal, a poikilotherm, they don't have, their cells don't need as much oxygen, as many nutrients, and so their circulation does not need to be as efficient and kind of well dialed, I guess, as the human heart. So as we get into physiology here, we've got a few different things to look at. Let's start by reminding ourselves, let's see if I can get this to advance, there we go, about cardiac muscle. So one of the strange things here, right, is in cardiac muscle, there's actually two different cell types, and you're not going to see them differentiated in a picture or anything. But basically, some of the cells in the heart are contractile, right? They're actually doing actin-myosin cross-bridging, just like we remember in skeletal muscle. But some of the cardiac muscle cells are actually conducting cells. These cells have become specialized in kind of this control and coordination of the heart. This is what we refer to as the intrinsic conduction system. This is how we are going to see action potentials travel through the heart. So a lot of people get confused and they think it's a nerve that's carrying, say, the action potential from the pacemaker to the rest of the heart, but those are actually just specialized cardiac muscle cells. So I always think that's kind of fascinating. And then the other thing that makes this cardiac muscle really special is the fact that it's autorhythmic. So it can contract on its own. Your heart does not need the nervous system or the endocrine system to tell it to contract. We will see that they absolutely play a big role in regulating the heart, but you can pluck the heart beating from a body, and if you put it in the right conditions, the right ions and nutrients and everything in like a little bath, it will just sit there and keep beating, right? It does that on its own. It does not need the nervous system. So I'm always like, that's so crazy. So let's see. Those are basically the same picture. So when we think about this rhythmicity, students struggle with this thought, and I think I understand why. So what we're going to see is we are used to there being like a resting membrane potential. This is a good review, like a resting membrane potential. And if a stimulus reaches threshold, we would get depolarization followed by repolarization, and we would go my marker here. We would go back to a resting membrane potential. But notice this resting membrane potential is not stable. It doesn't sit there at -70 or -90 or whatever and wait for a stimulus. It is always trending back up to threshold. It's slowly drifting towards depolarization. And so basically all that means, if you look at this on like an ion level, is that these cells are leaky. Okay, and so there is always just sodium leaking into the cell. Yeah, I guess it's sodium. Sodium slowly leaking in that's leading us up towards threshold, and once we hit threshold, we get depolarization, where more sodium and also in this case calcium are going to come into the cell and cause that depolarization. So when you think about autorhythmicity, it really comes down to this idea that they do not have a stable resting membrane potential. right? They're slowly drifting towards depolarization. So you get this spontaneous depolarization. And what we find is we have the fastest spontaneous depolarization at the SA node. So the SA node, or what you've referred to maybe as a pacemaker before, is this collection of cells in kind of the back upper wall of the right atrium. And this is just the group of cells in the heart that's the leakiest. So it depolarizes the fastest, and then it's going to direct the rest of the cells to go ahead and depolarize, right? So once it depolarizes and we get that, we start an action potential. We start sending that message kind of across the heart. And so normally that would actually want to depolarize at around 80 or 100 beats per minute. And what we'll end up finding is that the parasympathetic nervous system is actually constantly kind of telling the SA node to chill out. But what you can have happen sometimes is another set of cells, for whatever reason, maybe injury or whatever, starts depolarizing faster than the SA node. And so you get what's called an ectopic heartbeat, a heartbeat that starts where it shouldn't, right? And so that group of cells is going faster, and it's going to tell the rest of the heart to depolarize, but then you don't have that same input from the parasympathetic nervous system. Anyway, they're a pain in the butt. Doesn't happen that often. Okay, so if we have an idea now of kind of what that autorhythmicity is, let's take a look at how the heart is going to kind of run itself. And so we have this, what they call an intrinsic within this conduction system. And so again, this all starts up at the SA node, nice little number 1 right there. So the SA node, again, in the rear wall of the right atrium, its inherent depolarization is the fastest, something like 100 beats per minute. The parasympathetic nervous system actually uses the vagus nerve, cranial nerve number 10, do you remember that one? To basically inhibit, right, slow it down. So then what we're going to see happen is as we get a depolarization starting from the SA node, it's going to travel across the atrium, the walls of both atria, right? So it's spreading through the contractile cells of the atria, this depolarization is, and it's also going to then eventually get itself to the AV node, marked here with the number 2. All right, so we got SA node up here, and then in the atrioventricular, right? So sinoatrial node, atrioventricular node, and that kind of makes sense, right? It's going to be in this wall between the atria and the ventricle. It's kind of in the floor of this right atrium. At the AV node, this action potential, right? Remember, an action potential is just like this spread of ions running across the wall there, a depolarization running. It slows down kind of upon arriving at the AV node. The conducting cells are actually getting a little bit smaller in diameter, and that slows down just like in nerve cells. The smaller one goes slower. And you actually then get this kind of delay happening. So it actually takes, and when I say delay, this is like 100 milliseconds. This is super quick, but it is a little bit of a delay here at the AV node before we're going to pass it along to the bundle branches. So this is actually really nice. What this delay does is it gives the atria a chance to contract, right? And remember, the ventricles are still open and relaxed. We have a little pause at the AV node, and then we're going to send the message for the ventricles to contract. So from the AV node then, we're going to send this action potential down the septum, down the wall between the ventricles, and we call this the AV bundle, right? This is the AV bundle, and it then splits into the bundle branches. And so this action potential is running down here, right? It goes all the way down to the apex before it kind of turns around and heads up what we call the Purkinje fibers, right? So we're going SA node, AV bundle, bundle branches, Purkinje fibers. Okay, But the cool thing about this is now when we actually send the action potential out to the contractile cells of the ventricles, it's going from the bottom up. So we get that ringing motion, right? Because we want to push all of the blood out of these ventricles and up into things like the aorta and the pulmonary trunk, right? So same image there. So this is kind of what it looks like. Right, so here's the SA node. It's going to depolarize first, and that wave of depolarization is going to spread across the atria. It's going to reach the AV node, but there's our little 100 millisecond delay, right? So now the atria are contracting, filling the ventricles. We see this now spread down the AV bundle, the bundle branches, eventually reaching the Purkinje fibers, and now we see the contraction, that purple wave kind of moving up the ventricles. Okay, and so that is what that electrical activity of the heart really looks like. Now, we're used to visualizing that in an EKG. And I think that's one thing that's super important for you to realize is an EKG is a measure of the electrical activity of the heart. So it's not really measuring the contraction. It's actually measuring all these conducting cells and how well they're moving that action potential. And so what we see here on our kind of normal EKG or ECG, same thing, electrocardiogram, in German, cardios with a K. So we call this the P wave, and that indicates the depolarization of the atria. That is followed by what's called the QRS complex, and that is showing us ventricular depolarization. And then over here, we get the T wave, which is ventricular repolarization. So sometimes people say, well, what happened to atrial repolarization? But notice how tiny the depolarization wave is, right? So think about ventricular depolarization as this huge wave, repolarization is tiny. If this is atrial depolarization, repolarization is this tiny little wave, and it's actually kind of buried under this QRS complex. So if you are working in cardiac nursing, if you're a cardiologist, if you're an EMT, paramedic, those sort of things, you can take entire classes on interpreting EKGs. They're pointing out here a lot of these different intervals, so the lengths between these different timing of events can actually tell you a lot about what's going on in the heart. I will also say an EKG that they would give you at the hospital or in an ambulance is a 12 lead. When you look at this printout, this is a single lead. All of those other leads are kind of showing you different angles through the heart, and so you can get a lot of information on where the damage may have occurred there. Okay, so that kind of covers the electrical conductivity of the heart. Same image, this one is from your textbook. Now let's switch and think about the other set of cardiac muscle cells, and those are the contractile cells. In fact, the majority of the cells in the hearts are the one doing the contractions. Like 99% of the cells in the heart are doing contraction. And again, this is very similar to skeletal muscle. Cardiac muscle is striated, which tells us we have sarcomeres. We're using, remember, sliding filament theory, actin crossing over with myosin. The action potential, when it reaches that cell, it really means that calcium is dumped out all over those myofibrils. The calcium binds to troponin. Do you remember all of this, right? Which was on the actin, allowing actin-myosin cross-bridging. So there's a ton of similarities with skeletal muscle, and if you're like, I don't remember that already, might be a good time to kind of flip back and refresh yourself. But there's some really important differences too. So cardiac muscle is autorhythmic, right? It has that unstable resting membrane potential. When one cell contracts, all of the cells contract. That's very different than skeletal muscle. And then we'll also see it has this really large absolute refractory period. Okay, so let's look at this. So we have our kind of resting membrane potential here though, but not super solid. But we're about negative 90 millivolts. That's a little lower maybe than skeletal muscle, right? But just like we would expect, when the action potential reaches this cell, remember this is just coming through gap junctions now, When we reach threshold, right, these voltage gated channels are going to open. Sodium comes rushing in, right? Real quick, just a reminder, right? Remember resting membrane potential? You had that slight negative on the inside of the cell, slight positive on the outside of the cell. And since they're a different charge, we said this is polarized, right? So depolarization, when you see this line shooting up, it's because positive charges are rushing into the cell, right? So sodium is entering the cell, and that is what we see as this depolarization. And so very rapidly, these voltage gated channels are letting enough sodium in that we're going from like negative 90 millivolts up to 30. Okay. And then in cardiac muscle cell, this is what looks super different than skeletal muscle. We enter this plateau phase. So when we reach somewhere around positive 30 millivolts, the voltage gated sodium channels close, right? We actually start pumping some of the sodium out. So you see this little dip here. But then voltage gated calcium channels open, right? So depolarization is really caused by sodium. This plateau is caused by calcium. So as calcium starts flowing in, right, those are positive charges. It's holding us at this same level, right? It's not letting us repolarize. This calcium, do you remember where all that calcium was in the skeletal muscle? Which organelle? If you said sarcoplasmic reticulum, or SR, you were correct. In cardiac muscle, you have calcium from the SR and also from extracellular fluid. So one of the things you'll find is if someone's blood calcium levels get off, you see it first in cardiac muscle. Okay, so that membrane potential anyway is staying nice and high here, up around 0, and it's this plateau. Finally, after all of this, 200 milliseconds, like that's so long, we finally get to repolarization, and just like skeletal muscle, this is due to the efflux, the exiting of potassium. Because remember, potassium is your main intracellular cation. And so as we depolarized, right, and this became positive along the inside of the cell, now if potassium leaves, right, we can kind of start to reestablish our negative on the inside of the cell. So the potassium channel's open, potassium is leaving, and that's starting to work to restore resting membrane potential. Now, we have a mess to clean up, right? We got to get calcium back out. We need to get sodium back out. We're eventually going to want to get potassium in. So we got sodium potassium pumps and also some calcium ion pumps working here. Okay. The key thing here, right, is that this difference in cardiac muscle, the fact that calcium entry gives us this plateau, the key thing here is that we have a longer absolute refractory period. Remember, that means that is a period of time where no stimulus is strong enough to start another action potential. So that is going to give the heart, I suppose, like a maximum heartbeat. You can only contract the heart so many times. Okay. It also means that you never get, remember in skeletal muscle, it was like you had like a twitch if there was a single stimulus, and you needed like stimuli of a certain frequency to start getting like wave summation and actually being able to do work. We don't have that happening in cardiac muscle, right? So there's no tetany of cardiac muscle, which is also good, right? We want to keep the heart contracting. I thought this was a nice image. Again, sorry, this is out of my old textbook, but a really nice image comparing on this side skeletal muscle, and this panel over here is cardiac muscle. So notice, I'm kind of making fun of like, man, look at that absolute refractory period of 200 milliseconds, but that is actually much longer than the absolute refractory period over here in skeletal muscle. This also very clearly shows the plateau that we don't get in skeletal muscle. And also we can produce similar tension, similar force with cardiac muscle, but it's a little bit kind of longer, it takes longer. Okay. And I threw this in just in case you weren't going to flip back and look. I'll make sure I have this PowerPoint presentation up for you. You can look back. at skeletal muscle. Last thing I wanted to say about the cardiac myocytes, right? The actual cardiac muscle cells, the contractile cells, is if you think about their physiology, right? They need to be able to contract over and over and over again. We talked about the fact that we have this whole coronary circulation set up to feed the myocardium, right? They need lots and lots of oxygen, right? Cardiac muscle does aerobic respiration. They need oxygen. These cells actually have a special protein called myoglobin, kind of like hemoglobin, but it's in the muscle here, to help pull oxygen into the cells. You're going to need a really rich fuel supply, so plenty of glucose, glycogen, but really the heart's very good at using fatty acids. So even if you're out of glucose, you're like bonking, right? Your brain's not working anymore. Your heart will just use fatty acids, right? But we need aerobic cellular respiration. Okay, we're getting there. So we looked at this briefly in the last video, but let's talk about the cardiac cycle again here. In your textbook, this is figure 20.18. I like this image a little better, so I'm going to talk you through with this one, right? So basically the cardiac cycle, we're going from the beginning of one heartbeat all the way around to the beginning of the next. That is a cardiac cycle. And what we're going to see is that we get this brief pause between beats to allow chambers to relax and refill. That's what we see happening over here, right? So diastole, again, is relaxation, low pressure. Systole is contraction or higher pressure. So we start out with atrial systole. Again, the atria are helping gravity push blood through these atrioventricular valves and down into the ventricles. This is going to be important. One of the things it does, atrial systole does, is help determine what we call the end diastolic volume. With the largest, at the end of ventricular diastole, at the end of its relaxation phase, what is the max amount of fluid in the ventricle? So atrial systole is kind of that topping off that makes sure the ventricles are full so that we have a good end diastolic volume, or EDV. Okay, so then we move into ventricular systole. Okay, so notice as the blood starts to push up from the apex of the heart, those atrioventricular valves close, right? So that ventricular pressure is greater than the arterial pressure, and that's going to close these valves. You enter this period of time where you're in what they call an isovolumetric contraction. The pressure in this chamber is increasing, but there are no valves open at this point, and so there's not actually a change in volume. So isovolumetric, kind of like isometric exercises, you're stationary. This is going to be isovolumetric. Then, kind of in the second phase of ventricular systole, we get that actual ventricular ejection where we push blood, right? We actually overcome any resistance and we open those semilunar valves. The amount of blood that the heart pumps, right, the amount that is ejected there is called the stroke volume, right? So stroke volume, the amount of blood ejected from that ventricle. And typically it's around 60% of that end diastolic volume, that actual biggest volume that the ventricle holds. Okay, as the ventricle then enters diastole, as it begins to relax, we're going to see that backflow, right, in these great vessels is going to close the semilunar valves, right? And then we talk about whatever's left in the ventricle after that ejection as end systolic volume. So basically up here, when the ventricle is at its fullest, we'll have end diastolic volume, and then whatever's left after systole, at the end of systole, is end systolic volume. Those are going to be important here in a minute. That's why I'm writing them out for you. Okay. So we enter ventricular diastole, right? The ventricle is relaxed. Once that pressure drops below the pressure of the atria, those atrioventricular valves open again, and now gravity, right, is basically bringing blood through. Both chambers, all chambers, atria and ventricles, are relaxed, and blood's just going to flow in. Okay, so again, both here ventricular diastole goes all the way to here, and so does atrial diastole. Look at that. Most of the time, the atria is relaxed. Okay, with me? I hate not doing this in person because this is like, oh, what is she talking about? Okay. This is what's happening over and over and over, right? 100,000 times a day. Okay. This image, and I'll show you, the image in your book is 2019. I don't like it as much. It's not bad. This is just the one I'm used to. We're not going to get too into this, but I think this is kind of a crazy image just to remind you, right? Here is your EKG or ECG out reading, right? So we know when the different electrical activities are happening. But remember, I said that is just measuring electrical conductivity. So now this whole panel here is telling us when the pressures are changing. So it's telling us something about the contraction. And I like how they kind of laid out here, like who's relaxed, who's contracting. And so you can kind of see it, right? This huge amount of pressure is coming from the ventricular contraction. So this is kind of fun. It shows you when valves are opening, closing. And then also a reminder that, right at the end of ventricular diastole is when the heart is the most full. And this panel down here, we're looking at volume. That's your end diastolic volume. And then after this ventricle contracts, here's our end systolic volume, right? We didn't get all of it out, but a lot of it. Okay, I won't belabor this. I think it's kind of a fun graph if you have time to kind of sit down and look at it. Okay, cardiac output. We are in the home stretch here. So cardiac output is the amount of blood, the volume of blood pumped by the left ventricle in 1 minute. Okay, that's our super nerdy definition of cardiac output. More important to understand, though you should know that, right? It's the amount of blood pumped by the left ventricle in 1 minute. But more importantly, right, that tells us about blood flow to peripheral tissues. Do we have adequate output by the heart to perfuse our tissues, to deliver the oxygen and the nutrients they need? So cardiac output, you can actually calculate, and this is heart rate times stroke volume, right? So basically think about, right, heart rate, but then stroke volume was how much blood we pushed out of the ventricle, right? So truly, what was the end diastolic volume minus the end systolic volume, right? So what was this change? That's the stroke volume. So when we think about cardiac output, we've got all sorts of factors to think about, right? Not just heart rate and stroke volume, but all the things that maybe affect heart rate and stroke volume. So with heart rate, the two big things here, the biggest thing I would say is probably this autonomic innervation. So remember the autonomic nervous system, we're talking about sympathetic and parasympathetic nervous system. So the sympathetic nervous system, right, is going to be using things like norepinephrine to help open sodium and calcium channels and really encourage depolarization. Get that out of there. Right, so the sympathetic nervous system is opening sodium channels, opening calcium channels, and trying to get depolarization. So that would increase your heart rate. The parasympathetic, we already mentioned that it's constantly trying to calm the SA node down. And basically how it does this is it's releasing acetylcholine, right, on the heart. And that acetylcholine is actually opening potassium channels. And so as potassium is leaving the heart, that is actually putting us into like a hyperpolarization. So it's actually going to be a little harder to get our action potential to go. Again, the parasympathetic nervous system uses the vagus nerve to deliver this this information, right? It brings the impulse, the pulse rate of the SA node down. And then I guess I would also say that both of these are really controlled, sympathetic and parasympathetic nervous system, are under the control of the medulla oblongata. If you recall, the medulla has what are called the cardiac centers. And so it's getting information from chemoreceptors in the body, and then also baroreceptors. That information is going to these cardiac centers in the medulla, and it's helping decide, okay, do we use sympathetic to increase heart rate? Do we use parasympathetic to calm things down? Okay. Hormone-wise, right? The endocrine system can also play an impact here, right? Particularly, again, we think about epinephrine from the adrenal medulla and how that might increase heart rate. Less drastically, thyroid hormone, right? Its ability to increase kind of base metabolic rate, that will increase your heart rate as well. Okay, so that's the heart rate side, and that's actually maybe the simpler side. The stroke volume side, people often have a hard time picturing it, and so I love this image. Again, if you think about this as the cardiac cycle, right? End diastolic volume, right? When the ventricles are at their fullest, how much are they holding? That's the end diastolic volume. And here we see the pumping taking place, right? So we're squeezing the blood out, and we are left with an end systolic volume, right? We didn't get rid of all of it. And so the question is, how much did we actually move? That is the stroke volume. So you can influence end diastolic volume and end systolic volume in a couple different ways. So let's think about this. So if you wanted to increase stroke volume, this gets people too. If you want to increase stroke volume, do you want to increase or decrease end diastolic volume? To increase stroke volume, do you want to increase or decrease end diastolic volume? You want a larger end diastolic volume, right? You want to fill up this pump more if you want to push it out to the body. So a couple things can increase your end diastolic volume. Things like increased filling time. So actually a slower heart rate is going to give you more time for ventricular diastole to occur and for that filling to take place. The other thing we get is something called preload. So having more blood volume filling the ventricle is actually going to stretch the heart muscle a little bit. And this actually is going to give us ability to contract better, right? That's going to help us increase our stroke volume as well. And those are definitely related, right? Preload and a longer filling time, those are definitely related to increasing that end diastolic volume. How about end systolic volume? If you want to increase stroke volume, the amount of blood you're pumping, would you want to increase or decrease end systolic volume, the amount you have left over? You would want to decrease that, right? You want as little as possible left in your pump because most, what you can push out goes to the body. So you want to decrease end systolic volume. This is going to come down to a lot to the contractility of the heart. So again, we run into the autonomic nervous system. So the sympathetic nervous system will actually help the heart contract harder. It's what's called a positive inotropic effect. It actually increases the contractility. It increases the calcium available to the heart. The parasympathetic has a negative inotropic effect, and that's going to decrease the contractility. So sympathetic nervous system is going to decrease end systolic volume. Parasympathetic is like, chill out, heart. Like, you don't have to push all the blood. Okay. And again, preload kind of comes in here on this side as well, because remember how we said, well, that's actually stretching the heart. So just like skeletal muscle, you run into this where if like the actin and myosin are already like majorly overlapped, you can't get the contraction. So a little bit of stretch actually is going to help the contraction. It's called the Frank-Starling principle. And so sure enough, if you increase that preload some, you get a better contraction, better cross-bridging, better tension production through the Frank-Starling principle. Okay. And then the last thing to consider, I suppose, on end systolic volume, right? So we can decrease end systolic volume by having a good preload, right? Which leads to good contractility. Sympathetic nervous system can also improve contractility. The other thing to keep in mind on end systolic volume is that afterload has a big influence here. So the afterload is the amount of force needed to open those semilunar valves. So it's a measure of like resistance from the bloodstream. So what you'll find is that someone who has atherosclerosis or some kind of blockage of their blood vessel is going to have a lot more resistance, and it is going to be hard to get to that low end systolic volume, right? The ventricle pumps, and there's so much resistance, so much afterload that it doesn't actually move a lot of blood. Okay. So that's the way I think about, right? How do you improve that cardiac output? How do you improve that perfusion, right? You can use both heart rate and stroke volume. And I will say what gets super complicated, and I love that the medulla figures this out, the medulla oblongata figures this out instead of us, because it's not just having the highest heart rate possible, because you can get the heart beating so fast that it doesn't have time to fill, right? And so you would decrease the end systolic volume. So there's like this sweet spot, right, where you're actually being the most efficient. Okay, and your body is constantly adjusting that, right? You run up a flight of stairs. Okay, how did we change heart rate? What did we do with stroke volume? All that. Fortunately, we don't have to think about it except for in this class and in your future career. But you don't have to think about it to get up the stairs. Your textbook has a very similar outline. It's just not in that picture form. So again, things affecting cardiac output, they're running through things like sympathetic, parasympathetic stimulation, preload, all that kind of stuff. So if you're more linear, feel free to use that. This is kind of the way I think about cardiac output, kind of in a maybe a tabular form. There's inotropic, if you were wondering what I was saying earlier. I know it's pronounced like there's an E. Oh, this Bainbridge reflex I didn't mention. Basically, all this means is that as it's a reflex, right? It doesn't have to even go to the brain to figure this out. An increase in venous return automatically increases the heart rate here. So think about that. You went up the flight of steps, right? You started pushing all that blood out of your leg muscles. It goes to the heart, and that immediately picks up your heart rate. So there's some really fun stuff there. Okay. So honestly, these last kind of four, I've got one more. These last four images kind of all get you to the same place. Ooh, that one's kind of fun. Lots of arrows here. This one is only dealing, obviously, with stroke volume. So definitely this whole concept of cardiac output is I would say, is the most challenging aspect of this chapter, right? Hopefully lab is helping you get down more of the anatomy, and it's this physiology part. So definitely like look this through, take the time to try to think about this, because some of this just is sitting down with these graphs, thinking this through, maybe thinking about some real life examples, but we'll definitely have time on Thursday. We can talk about this some more. Okay, have a good one.